video for the notes for nuclear chemistry. Alright, so when we go through here, there's different ways to look at the symbols. So the X is going to be your nuclear symbol, so either like a carbon or a lead, things like that. And then the X is going to be, the A here, this A, is going to be your mass number. And the atomic number here is going to be the Z. This is the atomic number. Alright, atomic number. And so you can see here the mass number, there's a different way to write it with the atomic number next to the symbol. So for instance, like that, carbon 14. This is the A. Alright, and then the Z number is the atomic number, the number of protons there. So two different ways to write it. What are the charges on the protons in the nucleus? Obviously, you guys know that it's positive, and the neutrons are 0. So here's a question for you. Why do the protons not separate? How about that? Because they're all positively charged, right? And you know from playing with magnets as a kid that like charges repel and opposite charges attract. So there's a force. It's called the strong nuclear force. And the nuclear force, it exists between the protons and the neutrons. Oh, there's no S there, force. And it's between the protons and the neutrons, okay? And what it does is it keeps the nucleus together. It holds the nucleus together. It's like glue. It's one of the 4 fundamental forces. Magnetism, the strong and weak nuclear force, and gravity is the other force. What is a nuclide? A term, alright, just to describe the nucleus of a particular isotope. Alright. Of an isotope. Okay. So now we come down here, radioactive decay. Let's look at why things radioactively decay is because they're unstable. And we'll talk about a band of stability in a second. You have the alpha particle, which we talked about in class. Kind of looks like that. It's the Greek symbol alpha. It has a positive 2 charge. Why? Because it is a helium nucleus. So it weighs 4 because it has 2 protons and 2 neutrons. So the 2 protons make it positive. It's pretty slow in how fast it moves, okay? Because it has so much mass. So it would have 2 P's and 2 N's, and they'd all be, bunched together, and they'd be flying across space. It has low penetrating power, so it's not extremely harmful radiation, not like gamma. It could go through like paper, or it could go through skin. Alright, that's what it could go through. Then you have beta. And the beta kind of looks like that. That's the symbol for beta. Beta has a charge of -1 because what it is, it's an electron. It's an electron, and it's going to be moving fast. And it has medium penetrating power. So its strength, as far as getting through something, is stronger than the alpha particle because it's moving faster and it's smaller as well. So you could go through maybe a book, or you could go through a piece of wood, things like that. Alright? Then you have a positron. Now, the book lists the positrons, so you have 2 different symbols. This is one way to write the positron. Okay, the book lists the positron also as this. Or you could list it like this. 0 + 1 beta. So the book lists it like that. Our notes list it like that. It's a positively charged electron, so it's going to be very similar to this, to the beta particle. All right, positively charged electron, and it's also the same here, right? It can go through. It's got medium strength. It can go through a book or wood. Same type of strength. And gamma kind of looks like this in the book. All right, like a Y mixed with an R, like a cursive R. But then the notes have it written like this. Which one is correct? I'm not really sure, to be honest with you. But it has a zero charge. It can go through, it has really high frequency, so it's very powerful. It's the most powerful of all of the electromagnetic radiation. It could go through lead, all right? It can even go through thick concrete, all right? And it is electromagnetic radiation. Okay. So that's the thing we want to avoid the most on the electromagnetic spectrum is gamma rays. All right, and you know a neutron just is a neutral particle, okay, a symbol N. It would have a weight of 1, a charge of 0, and M would be its symbol. It would not be applicable to to its penetrating power. And an electron capture, just put the symbol E1, or like this, like the book shows it, and it doesn't really have penetrating power either because it's going to be absorbed by the nucleus. So the nucleus takes an electron from an inner energy level. Okay, and let's just go to the next one here. Oh, and we also have protons, right? Which obviously you guys know are P. They're positive. If you wanted to write it as a symbol, you could write it like that, or you could write it like this. Either one of these is fine. All right, cool. Let's go to the next page. There is your band of stability. All right, so your band of stability tells you where you're going to be stable. This is not a chart that's in your book, but tin 100. Tin has 50 protons. So here's 50 protons. If you zoom in, it says 50 protons, and this is neutrons. And here's 50 neutrons. And you draw a line over from 50 to 50, and bam, there you go. It is within this line, this band of stability. Therefore, yes, tin 100 is stable. If you look at neon 25, neon 25 has 10 protons, and therefore it would have 15 neutrons. And you're looking, you're like, well, it's kind of darn close to being outside the band of stability, like if we drew a dot there. So we could say, no, but it's hard to tell with this graph. You have to zoom in closer and see. But the point of this table and these questions is if we had, let's say we had tin 130. That means we would have 50 protons and we would have 80 neutrons, and bam, it is outside the band of stability, so this would be unstable. So that's the whole point of this band of stability, to show you what's stable and what's not. If it's not stable, it will radioactively decay. Okay, so here are the 4 types of reactions that we have in our nuclear chapter. The first one is alpha decay. It's going to give off a helium nucleus. So uranium-238 is unstable, so it gives off, and maybe we can see that up here, if it's at 92 and it weighs 238, you got to go all the way up here to around like 140, and we go off the chart. That's all right. Okay, so helium nucleus. It's going to weigh 4. It's going to have a positive charge, 2 protons. What is uranium going to turn into? Well, this is how much it weighed, 238. It lost 4 AMU. It lost 2 protons, 2 neutrons. So now it weighs 234. It had 2 protons removed, so it doesn't have 92 protons anymore. Now it has 90 protons. What element, look at the periodic table, has 90 protons, and you will see that it is thallium. And that's how you go through alpha decay. Let's look at another one. Here you go. Pa224. Oh, I'm going to pause this. I need a periodic table. All right, now that I got my periodic table, I see that TH is not thallium, it is thorium. And now that I'm at Pa, Pa has an atomic number of 91, and its chemical name is protactinium. Awesome, good times. All right, so now protactinium is going to go through alpha decay. That means it's going to lose a helium atom, same thing, or a helium nucleus, I should say, not an atom, excuse me. So it's going to be positively charged because it doesn't have the electrons. What is or are the products? So there's the helium nucleus being lost. So the protactinium lost 4 AMU. So doesn't weigh 224 anymore. It weighs what? It weighs 220. And does not have 91 protons anymore. It lost 2. So now it has 89 protons. And if you look at the periodic table, you have actinium. Okay, AC, that is element number 89, and that is your product when it goes through alpha decay, when protactinium goes through alpha decay. Beta emission. When you go through beta emission, you are losing what? You are losing an electron. There's your electron that you lose. All right. So if this is 1 and it has a charge of 0, then it becomes, it stays 1. This number does not change because the electron weighs essentially nothing. But this had a charge of 0. This was a neutron. This N here stands for neutron. The neutron turned into what? It turned into a proton because it's not neutral anymore. Okay, if the neutral had equal positives and negative and it lost one of its negatives, now it's positively charged and it turned into a proton. All right, because it's a negative, went away. All right, so let us do this one. Carbon. Carbon 14 is going to go through beta emission. So here is the beta particle coming off. And what does it turn into? Well, it doesn't change weight because it still weighs 14 because the electron weighs nothing. But now it has gained, if you can zoom in here, this is a 6. It looks like a 5, but this is actually a 6. It doesn't have 6 protons anymore. Now it has 7 protons. Why? Because one of its neutrons turned into a proton, and now it has changed into nitrogen. Changed elements. Copper going through beta emission. Here is the electron that it emitted. All right, it still weighs 66, but it is not copper anymore. What element is it? It is now zinc, because one of its neutrons, it had 29 neutrons, it had 29 protons, and one of the neutrons turned into a proton. Why? Because the neutron was neutral and it gave away a negative, and when it gave away a negative, the neutron became a proton, it became positively charged. And that's how you do beta emission. There are more questions like that on your homework. Then you have beta decay. So you have, here you go, Pa234, which is element number 91. That's the protactinium, right? The protactinium going through beta decay. Well, it's still going to weigh 234. Oh, and I forgot to, there's the electron flying off. There's the beta particle. It's still going to weigh 234, but now it's going to have 92 protons because one of the neutrons became a proton and it turned into uranium. All right. Now let's go through a different type of emission, positron emission. Positron, positive, tron, it's a positive electron. All right. So PO 207, and that's polonium. Polonium is going to give off a positively charged electron. And when it gives off a positively charged electron, it still weighs 207, but now it actually lost a proton. So now it only has 83 protons and it became bismuth. Why? How did that happen? Because it had a proton which was positively charged, and let's say it had this positive, it gave it away, right? So let's say it had more positives than negatives. So the negatives were down here. When it gave away a proton or a positive charge, then the proton became a neutron because it was balanced, because it had the same amount of positives and negatives. So the way I look at it is like this. If I say a proton, let's say, has 10 positive charge and 9 negative charge, it is going to be positively charged. But here comes one of its positive charges going away, so now it has 9 positive charges and 9 negative charges. Now it's balanced, so it's not positive.